because we've noted and kept sort of say as something to pay attention to, the possibilities of context sensitivity of a lot of the ways that we use the words like that. And then striving for kind of objective facts underlying them. We're noting that when you have, if you think about the fundamental depth facts as graded, and that then when we talk about things being deep, we're sort of applying what might end up being kind of arbitrary cutoffs, that how deep you have to be to count as deep, right? I mean, when you're dealing with vague expressions, to sort of recognize fact that if the underlying phenomenon is graded, like in the tall, right? Well, you know, the tallest facts are objective. Right? Then you say, well, how tall do you have to be to count as tall? Tall enough to be, you know, if you're talking about NBA players, it's going to count as tall, it's going to be much higher than if you're talking about people who aren't. And so it could be one way of sort of keeping in mind that some of the ways the context sensitivity could arise could just come from that. The underlying facts are graded, and sometimes when we just say, this is deep and that isn't, we're applying kind of an arbitrary cutoff for them, gradation. And those cutoffs can change for contextual reasons.
And I think it's also the case that when we had this list yesterday of the things that the word deep might apply to, so we have theorems, proofs, concepts, definitions, and so on. And you know, as Marc pointed out in the last discussion period, capturing the right concepts is certainly one place where notions of depth come up. And I think there it really is the case that we're often thinking, you know, in direct comparisons. Right? We have a few different definitions that, you know, are sort of on the table. We're trying to hold them and figure out what the right one is. And you can sort of say, well, this one is better than that one in the sense that it's, you know, tracking whatever it is, you know, depth say that we care about it, without having to somehow, you know, put your foot down and say no. At the end of the day, this is the deep one. It's the deeper one on the table of the ones that I've come up with. I mean, I think that, you know, so Kat earlier made the connection to axiom choices in set theory, and there it often is also a comparative thing. I mean, so you have several potential new axioms on the table, and you know, not necessarily that you're going to be in a position to say this is the deep one, just that we have reason to think that this one is better than that one because it's somehow deeper or tracking something about depth in a better way.
I would like to ask, I wasn't here for the discussion when we had 1 through 6 up there. There were a couple of things I wanted to ask about that list. One is, I wasn't clear what 5 is and what objectives and prizing this is. And I know, Jamie, you explained it, but I didn't.
Well, I'm not sure.
Let me ask my both questions.
Gestured in the direction.
The other,
And then disavowed.
the other question was this: we had 3 there, we had Andy's very nice example of something that was 3 without 1 or 2 when 2 is read in the strong way. I wondered if people had a sense of, we've got a lot of examples on the table at this point, and I wonder if people have a sense of whether all those examples, well, where each of those examples might fall under 1 through 6, whether they all do. Maybe there's some examples that we take to be plausible, convincing cases of depth, or deep relative depth or something, but don't fall under any of 1 through 6. So I was wondering if we could sort of look back at the examples and see how at least some of the examples people might pipe up with about where they would fit in this picture, or not. So those are the 2 things I wanted to ask about.
We haven't necessarily agreed on which things are deep and which things are
Well, then
Some
maybe
people
that's
have-
where we should.
That may be where we should start.
Yeah. I wasn't sure whether we had decided that or not. Maybe Jamie, you can say that again about objective depth, objective.
Well, I'm not, the idea was just It was more just a point of clarification that if we're going to say that one of the things about a deep proof is that it shouldn't, in some cases, I mean, one of the signs, one of the ways it can manifest is that you're surprised, there's something that catches you
Yeah,
off guard.
that makes sense, it would be a.
And I just wanted to remark that, surprisingness, you can understand surprisingness as a kind of psychological fact, right? That, does it surprise you or not?
Yeah.
And I wanted to suggest, well, you want to be careful about that because, it can surprise you if you're feeling tired, it can surprise you if you have too much to drink, or if you're not paying attention, or it could surprise you if you've just kind of gotten used to it, or if you don't know enough. But then but you want to say, well, there are certain things that ought to be a surprise. That is, say that, and the example I used is when I'm teaching students, in the sort of advanced logic class, things like, the completeness there for the first order logic. I'm telling you ought to be surprised by this, and they're not. And I said, well, no, look, it really is surprising, right? You can learn more. You start understanding these poems, and then you'll be really surprised. The more familiar you become with it, the more surprised you'll be. And so I just wanted to say that we don't want to be too distracted by the idea of the psychological understanding of what it is to be surprising. That we can also have. There are just certain facts. When, I think Marc gave a construal, which I thought was, on reflection, really much more helpful than anything I said, which was that, you can have these these non-deductive conditions, these sort of non-deductive presuppositions that naturally come with a certain kind of study or a certain sort of subject matter, a certain kind of line of investigation. Like, say, a certain kind of family of assumptions that come with just dealing with natural numbers and investigating them, certain sorts of things you expect, so to speak, naturally. And relative to those, quadratic reciprocity is a huge surprise. Right? And that way you could say, well, it would be a huge surprise, objective, even if a lot of people didn't find it surprising. Right? Just because, well, its surprisingness comes out of certain ways of thinking that are very natural given the subject matter, and this seems to cut against the grain or clash with those ways of understanding.
Well,
No?
it still sounds to me like a way of detecting, maybe a pretty good way of detecting depth, or not depth is.
Well, I don't.
That's a
I
different.
certainly wasn't saying it. I mean, I don't think the suggestion is necessarily it's constituent. It's a way that depth manifests. It's a sign of depth.
Okay, so I was putting it with a pile with, we had a whole bunch of these things that were in a different pile that we sort of set aside. Hidden connections, we don't want to say they were hidden because that looks like it's just, how good's your eyesight, and transformative and surprising, interesting, and insight, and all those we sort of, I thought I'd put into a pile. I think Marc actually did at some point make that distinction between constitutive and,
Right.
what did you call the other pile?
Well, they were somewhere symptomatic.
Symptomatic, yeah. So I thought, that's why I thought 5 was really symptomatic rather than constitutive.
Yeah, sir, I'm not sure that we actually meant this as a list. I think this was meant to be a kind of list. Some of things could be sort of indications, not necessarily
Okay.
constitutive.
So I had understood this list to be a sort of the things that had come up before plus things that came up today that were at least potentially, as Bob put it, in the math as
Yeah.
opposed to in us.
Yeah.
And so something that's objectively surprising is perhaps, I guess I put it up because
Because that word
I'm wearing
objective
it.
is.
Yeah.
Okay, so, fine, then my question is the one about, if anybody has a pet example that interestingly fits in one of these or doesn't fit in any of them or something, I'd like you to know.
Well, there's one I was sort of thinking about concerning opening up a new field. And it was just a kind of an extension of an example that we'd already considered, because we also considered the examples where some debate about whether they could be deep or not, that end up closing off a field by, sort of, say, classifying everything. And so the example was the classification of finite simple groups. And then there was part of the dispute about whether or not that was deep or not, I think also involved the fact that, well, there was a bunch of different categories and they're kind of, maybe some of them were a little heterogeneous and that's not really the sort of thing you can repeat. And so I thought an example which would be like that, except it did bring out an underlying uniformity. And furthermore, it's called the fundamental theorem, and I think another, if it's called the fundamental theorem, how can it not be? But that's fundamental theorem of revealing groups, right? That every revealing group is isomorphic to a direct product of cyclic groups. And once you sort of say that, that's all you need to know about the structure. I mean, mathematicians, please correct me if I'm wrong, that sort of thing. It basically tells you everything you need to know about the structure of finite revealing groups. It also turns out that it brings out a sort of striking uniformity. It may well be indeed it's called the fundamental theorem, but it certainly doesn't lead you to do more research into the structure
No, it's a
of
kind of a
finite revealing
form,
groups.
isn't it a kind of a form?
Yeah, it has organizational power, right, exactly, and it also, I think, brings order to,
It's a three-dimensional
order
form.
from chaos, and so it increases the amount of order. But in doing so, it sort of it ends a line of research.
Well, I wasn't imagining that we were thinking that anything had to have all of these, that these were different ways, there are various ways of being deep. in
No, I was
research.
just putting this forward as, just.
I see.
We wanted examples of things that had some and not
Got
others.
it.
I think it came up yesterday. I don't know if anyone would consider this a good example, but Cantor's diagonal lemma maybe is objectively surprising. Certainly it's surprising when people first hear it. Opened up a new field, but it doesn't seem to have properties 1 through 4.
Yeah,
Mhm.
good.
Mhm.
I think you can give it an impure proof using measure theory, for instance. That, any countable set has measure 0, therefore it's not a whole set of reals.
Yeah, but you're gonna say that it's deep regardless of that.
Yeah, I would, yeah.
Actually, in support of your statement, I would maybe move that we remove 5 because there are certainly things that are deep and are not surprising, and there are certainly things that are surprising and are not deep. So I'm not sure why we want that there.
Move, strike.
So we had a distinction from yesterday where we talked about things that were hashtaggy, that were characteristic of, but not constitutive of depth. So we might think that
But this one is neither.
well, I mean,
Because there are certainly things that are surprising and not deep, and there are things that are deep and not surprising, so.
well, yeah. So certainly we don't need it to be every time. Like it doesn't have to be perfectly characteristic. There can be things like the set of surprising things can be larger or just not. It can just intersect with the deep things. That's fine. I think the question is whether maybe there's a preponderance or whether it's a good flag to follow, something like that.
Well, can we get an example up here of a thing that's not 5 but one of the others? Actually, what do you have in mind when you say there are things that are deep but not surprising? Do you have a particular example in mind?
Deep and not surprising. Well, so for example, Faulting's proof of the Mordell conjecture. People would say it's not surprising. It was the expected result. The result was not surprising. The result was expected. There are many things for which there's a heuristic proof, but it's still very hard to find an actual proof. And so those are important results. The proofs are deep, but the result is not a surprising result. No one was surprised that the result was there are finitely many solutions to.
Are we slipping here between talk of the depth of the result and talk of the depth of the proof?
No, they're both the statement and the proof would be deep in that case. But the statement is not surprising.
Did the
Not sure
proof have?
was surprising, but it was deep.
Did the proof include innovative, unexpectedly?
It did include other things on this list, but it was not surprising.
I just wonder whether if the proof included particular innovations that would themselves be dare I say it, objectively surprising. That's what I meant
Well,
by
it
slipping
probably,
between.
may have opened up new fields, it had organizational power, it did bring in things from disparate fields, it did a number of other things on that list. And I think everyone in the field would say it was deep. But people would also say it was the expected result.
The expected result, but maybe not the expected way of proving.
Yeah, it's not something where you'd say surprising was one of the reasons that it was deep. That's it, let's say that.
Well, saying I don't know whether that's a list of
So I'm wondering,
things that make
what is
it
this a
deep
list of?
or.
What is this a list of? Because yeah, maybe that's the
Not sure,
question.
things we've been
Because-
talking about.
Because, if you could be deep and not surprising and surprising and not deep, then, that seems to me different from the other things in the list, where they're sufficient but not necessary.
Well, there's a
Yeah.
correlation, obviously, so these sets have some non-empty intersection, doesn't mean that one is contained in the other.
I thought we had decided that 5 was more of a symptom than a constitutive thing, and we were looking for the constitutive things.
That sounds like a
Didn't
second
we-
just strike.
Didn't we agree? What was that?
That sounds like a second just strike.
Oh, did somebody move it? Then I seconded it.
By acclamation?
I bet she moved it on the
Well,
second.
Well, bracketed anyway.
Did I move it?
Oh,
Second?
yeah, bracketed.
Yeah.
There we go.
All right, there we go. So, yeah.
One reason to keep it up there in some form or other is that it is connected in some ways to tying together disparate fields.
Yeah.
In that one of the ways that a result could qualify as the sort of thing that one ought to be surprised by is that it ties together fields that one wouldn't reasonably have thought were tied together. That would still make it, as it were, epiphenomenal rather than constitutive, but not unrelated. And it would still allow it not to co-vary strictly with any of the other things on there. But I don't have I'm not carrying a torch for number 5, I'm just pointing out.
But actually, the reason I didn't want to strike it off altogether is I can think of a number of fields of other citations where it was the surprising nature of the result that did it. And in fact, the modularity conjecture, right, the Taniyama-Shimura, that connection to Fermat's theorem was widely regarded as very surprising when it came out, right? So it's not constitutive, no, but I wouldn't want to throw it away because it seems to be the kind of thing that mathematicians pick up on occasion.
Well, also, there's another concept we haven't talked about much, but it might be worth just mentioning, for the record, is so to speak, naturalness. Especially if you've described certain conjectures as natural, certain expectations as natural, and relative to that, you might say, if you're working in a field, people who know the field to a certain, in certain ways, will regard certain conjectures as natural. And that seems to be certainly something that's part of, looking in from the outside, part of doing mathematics. And if you have some idea of what natural expectations are, you have an idea of things that contradict those natural expectations, clash with them. And so you might anticipate certain things which go against the grain of what you would expect, might be among the things that you would look for to be things that would reveal unexpected depth, not necessarily necessary and sufficient condition. But it might also, it ties into other fields.
So, okay.
No, go ahead.
I was just gonna say, one result that has been cited by a number of different people as clearly deep are Gödel's theorems. I'm not really sure how to think of them in connection with any of these things we've written down.
Well, maybe 6. But that's not the reason we think it's deep.
Well, I mean, this example that I cited, that every recursive predicate is arithmetic, it certainly fulfills 5 very nicely, and it's exactly this kind of objective surprisingness that Jamie was talking about.
Better
Because,
keep 5.
recursive is such a so much stronger thing, that objective, there's no reason to expect that this should be true. That's the best example.
But I think, doesn't Gödel's theorem also in some way fit one, that it's using, somehow bringing number theory into, when you Gödel number things, and then you say, well, okay, I can take all these, any statements, axioms, and, the language and so on, and we can turn this into number theory, and then we can do certain things, involving factorization that then can bring back and come to conclusions about.
I mean, the only
which
number
is the
theory that
theorems.
he needed is that every integer, can be written as a product of prime powers. I mean, how much number theory?
It's not that it's deep number theory, but it's the making the connection, using that connection to
We didn't expect that number theory could express
could be useful in
syntactic
Gödel's
operation.
logic,
Right.
yeah.
Yeah.
But is that why it's interesting, or is it maybe just that it is a surprising result, and I'm gonna retract my statement that we should remove surprising? Because I think surprising probably is important, that it was such a surprising result.
But part of the reason it was so surprising is because you didn't think you could prove a thing like that about logic.
Yeah,
And
no
it was
matter
only
how the proof
coding.
went.
That's what you're talking about, is the coding, the idea of coding up
Yeah.
was a connecting together.
Well, so I can confess to a shocking degree of ignorance at this point now. Does the coding idea itself spread out? Do we wind up coding? I know
Well, you
there's
do an
coding
awful
theory
lot
grudge
of
about money, but I mean,
logic,
having,
The whole idea of doing meta logic and
right, then that would seem to be somehow
6.
six.
Yes, I think.
Yes.
Yeah, the whole.
So it's not just the conclusion of Gödel's theorem, but somehow the idea of
Computability theory,
Absolutely.
computability comes out.
It's definitely 6.
Right.
Okay, so we think one, I mean,
We think needs.
6.
1, 6, presumably not 4 at least. Not 3.
You write 5 with brackets in it.
Okay.
When we discussed it before, I think we ended up with maybe 3. Because you could read it of one of 2 ways, right? Of either telling you there isn't order because of the
Yes.
unprovability, or telling you there is order because you learn an awful lot about the
Yeah.
model.
Yeah, and there's, and especially the fixed point property.
Yes.
If you sort of see the heart of the proof as being the diagonal line, you'd see that there are 2 things that are going on. One is the representability in arithmetic, and then there's the fixed point property. And if you focus on the fixed point property, that creates a lot of order out of kind of chaotic situation.
I'm gonna take a stand on 2.
You want to take a step?
No, I'm curious how we're supposed to think of impurity in the context of Gödel's
Well,
theorem.
there's a question, so if you think of Gödel's theorem as essentially about Campbell arithmetic, and you're drawing on arithmetic, then it's not pretty pure. But if you think of it as a result in logic generally, and you're using number theory, when you phrase it that way, well, then that sounds like impure.
I think you're equivocating on piano arithmetic. I mean, it's not a result. I mean, it is a result in piano arithmetic. It's the fact that it's about piano arithmetic, and it's a surprise that in piano arithmetic you can prove something about piano.
But how can something be pure?
What? Be shorter, is that what you said?
Pure.
Oh, well, because stuff about piano arithmetic we didn't think was piano arithmetic. We thought that was logic. We thought it was meta logic. We thought it was a whole separate, disparate field.
But there's a sense in which it's turned out that we could be even purer than we ever imagined. So there's nothing surprising, objectively surprising perhaps about that, but it doesn't seem like a failure of purity. Unless you think that it's turned out that you've been able to use number theory to prove the result of logic.
Yeah.
In which case, that was the sense in which it sounded pretty impure.
Yeah. I wouldn't say it's impure because of that reason. It was a fact about, a set of axioms.
Maybe it's 2 rather than 1 that should be
Yeah, so maybe really what we should have been saying here was two. It's not so clear that it ties together disparate fields.
No, okay.
I think there's a concept that's come up a number of times, which is not up there, which I think better captures what's deep about Gödel's theorem, and that's transformational. Right? This is the concept that Mario brought up a number of times in his talk, and I think that better captures what I think is deep about Gödel's theorems. Like, it does seem like it has a transformational effect on mathematics and logic, all of that.
And that's
Well, it
different from
certainly has.
sense.
Yeah, we had
I
a
mean,
couple of
I don't know if
things.
I'm right that that's what's really deep about it, but it's at least a concept I think is important that we didn't have up there.
Yeah, we had a couple of things from
Yeah.
yesterday's list that are not up there. One
Yeah,
of them is
right.
the one that to Hardy was the most important, which is having the many strata, which we said yesterday was layers of concepts
Yeah.
required.
Yeah, it might be worthwhile
Through.
bringing back
Yeah.
yesterday's list as well.
So layers or strata, standing on the shoulders of giants, the fact that, how many giants, that was, maybe John, Mr. Davis, how
Well,
many
but
shoulders?
But the reason for this list was to distinguish between those things that are in the math rather than just in our development of the math, and so that was the purpose of this. This list was not meant to be, this is what is depth, but that these are the aspects of depth that seem to be clearly not, first the issue was not psychological but in the math, but it's not clear whether, when you talk about transformational, when you talk about layers or strata, at least in the sense of standing on the shoulders of giants, then you are talking about human history, if not human psychology, and not what's implicit in mathematics.
Yeah, but the thing is that if we're trying to
Nothing's wrong with that.
Yeah, we're trying to fit these examples into our list, and if our list is just things that are in the math and not things that are more subjective, whatever, then we shouldn't be trying to force our examples into there, because it might be the reason that we call Gödel's theorem deep is because of these like subjective reasons, and not because of these the things that are in the math that we have listed up
Well,
there.
but that was the point, then we're gonna look at the ones that looked like they were objective and see if they actually captured everything.
Yeah.
And if they were missing some stuff, then we would say, well,
Then I
we're in
should
trouble.
pull transformational,
So you-
perhaps out of it, unless we wanna think
Yeah,
about whether or
so that
not
was the
that
idea,
is.
so you might say, yeah, well, this
Okay.
list is incomplete because, you can't get by with the objective ones, because Gödel's theorem doesn't. If we've got an example that can't be, that we clearly see as deep, we know that, and it can't be captured by the ones that we think of as being objective, then, well, then our list is a little bit in trouble, we have to rethink. But the exercise was, can we do it? And that's why I asked the question, are there ones that are clearly like that but won't fit?
So am I the only one here who thinks that these are not objective and that these are not just about the math, but about people? So some
I was just thinking
agrees
that
with me.
disparate fields, I mean, isn't that
Yeah, I mean,
our
all of
experience
these I
of
could
them
argue.
as how we learned about them, but they're actually joined.
Yeah, these are all based on the history of mathematics and the history of the field and what the people have done and the order in which we did it and who decided what was important and what we consider to be a field. The definition of what's a field is very people dependent, society
Although to be
dependent.
fair to Jim, I think you did say at the outset that insofar as we can make sense of disparate fields being part of the maths, then one deserves to be on that list.
One way to try
I
to think
didn't say that
about.
about the other things we dropped too, right?
One way to try to think about individuating fields, I don't know that it works perfectly, would be to look at the sort of goals and methods of, and conceptual concepts that are connected to a field. So it seems, that's why I was asking actually Mark about algebra, because it seemed like sort of algebraic thinking. So in algebra, you're trying to find a common structure in a bunch of things, and you use certain kinds of methods to do that. When you're doing set theory, that isn't what you're trying to do. You're trying to do lots of things, find a rich foundational framework for things and so on, and so you use other kinds of methods. And if you're doing analysis, it grew out of application, and really care about trying to get at the structure of Rn, and stuff like that. What else? Number theory. You're trying to get the structure of the standard model. I think about standard. So if you find something that connects together fields that are disparate in that sort of way, it seems deep. And the example that I think of would be, this is all just for one, it would be when large cardinals ended up telling you something about sets of real numbers. So you got something that really came out of analysis, and it was investigated by the early analysts of the early 20th century and so on, as parts of analysis. And then you got large cardinal theory that was really part of the whole sub-theoretic way of thinking. I want to make this thing as rich as possible, blah, blah, blah. And it turns out these things have consequences for that. It was surprising, yes, but I take that to be a symptom of a kind of a connection that is deep. Anyway, just a suggestion.
You can follow up. Oh, I didn't, you were about to say something.
I was just wondering why we don't put the strata depth on the levels. Is that really, Hardy is arguing that's the mathematics. That has nothing to do with people. It's the levels of mathematics, maybe not shoulders of giants. Let's not say shoulders of giants. Let's say concepts. We have scaffolding, we have mathematics built on itself. So I would say the strata.
That was the idea you had to.
What should I write? What is the? So if you remember last time I tried to write something like this, it ended up with 4 different iterations.
Want to give us lost
Layers of concepts,
Oh.
strata of
The
concepts.
strata,
Of mathematical.
Whatever Hardy said.
Yeah. Yeah.
Isn't that
Yeah, what
proof
Hardy said.
requires layers of concepts?
Well, what we said last time, one of the versions was layers of concepts required for, let's say, an insightful proof, but, or we said existence of multiple layers, so that was another version, so
I think it's connected to the definitional depth that I was talking about when I was talking about Fermat's last theorem. At least, I think that's what Hardy's saying. He's saying that strata, the deeper strata are defined in terms of the higher strata. I think that's what he's saying. I'm not absolutely sure though, he doesn't make it completely clear.
Of course, he was an analytic number theorist, right? So he's going to
Right.
like two.
Yes, yes, yes.
Well, the case of Hardy's criterion is complicated because he's talking about the prime number theorem, which he believed there could be no elementary proof on.
Right.
He says that a number of times, and then there is an elementary proof.
Right.
At that point, he was gone.
Right.
But others,
Yes.
but others like Ingham were not. They were.
Right.
Right. They claim that this throws all of the Hardy thought out. That was
Right.
the.
Right. That's why two bothers me a little bit, because I mean there's very general theorems in logic which say, given an impure proof, you can sort of get some normalization trick, get rid of all this higher order stuff, and you're down. You've got a pure proof, right? And I think that's probably true for a lot of mathematics, that you can purify a proof by doing this normalization stuff. Of course, the thing gets an awful lot longer, and it might be an incomprehensible proof, but to say that it requires an impure proof, I think is a little bit hard, and I agree with Andy.
But admits is very weak.
Maybe
right?
benefits.
That just invites some
benefits
ingenious person to give
Right,
you
that's
proof.
different. Right, requires and admits is very different. I agree. Yeah.
I'm suspicious of two, I've got to say, because I think it's not clear to me what it's doing that one doesn't do, unless we're confusing the results, deep resolve, and proofs.
Well, to some extent, it depends upon how it ties together as interpreted. For instance, if two were changed from an impure proof to an impure explanatory proof, then two would be rather different from the way it is now.
But then
I'm not recommending it, I'm just
But then
pointing
impure
it out.
gets, you see, Andy said something which made me think what I didn't like about it too. Analytic number theory is impure. It's kind of what it says, these two things jammed together. But that's if we've got the fields carefully defined in the first place, right? There's analysis and there's number theory and there's a hybrid.
Yeah.
But why would you do that? Why would you say these are separate fields that have somehow come together? What's our definition of field here that allows us to do that?
Yeah, for me,
And
analytic number
maybe we
theory
should
is
just
really-
say, hey, it's all analysis, guys, and you're just one bit of the same.
Well, so
You're
you-
one bit of a field or another bit of a field. So I'm really unsure about the impurity of analytic number theory, whereas I admit, of course, that sometimes very strange things walk into a proof in order to make it work. Things that you really because I do want to say there are fields. Mario reminded us differentiable in real analysis is way different from differentiable in complex analysis. So I do want to say there are fields, but I'm getting very
But you don't want to say analysis is a separate field from number theory?
I want to say there's a lot of overlap, and I start to get worried about what a field is at some point. How do I know
Analytic
I've
number
got
theory is a field.
I don't know. I mean, there's a working definition. And number theory is about the integers, analysis is about inequalities,
Well,
algebra is about equality.
Talking about these things.
Is this a place where the difference between going after depth versus going after deeper then would help, because we might not be able to agree on, as it were, these are different fields versus the same field, but we might be more inclined to agree on when they're, as it were, closer to being in the same field and when they're further apart. So you had, what, two parts of analysis, or 2 parts of number theory. We might be more inclined to think that they're being nearer together or further apart is an objective matter, even if we're not sure that they're in. That's far enough apart to count as different fields. Was that clear at least, even if it was not convincing? You're looking at me blankly, so I'm not sure.
Jimmy?
Well, just to follow up on the suggestion, which is very compelling, that there's this historical and very contingent dimension to how fields, arise, and how it is that we end up, grouping together some things and not others. But just as kind of a counterweight to that, also sort of suggest this that there really do seem to be, there you can point to different ways of thinking, different types of reasoning that you can point to in different subfields, that maybe there's a lot of overlap and maybe there's a lot of cases where one gets borrowed in the other, but you can still sort of point to it and say this is reasoning of the following type, and if you look carefully, you can make a case. And what I'll try to explain what I have in mind is that this is the time of year when I become the most important, not important, but the most popular, most popular person in the math department, because everybody needs an outside reader, and or every PhD student needs an outside reader, and so suddenly these emails come up, and so I end up sitting in on a lot of PhD committees, and I really come away with this impression often, especially when the fields are nominally close together, like commutative algebra and algebraic geometry, that despite the apparent superficial affinities, there really is a different way of thinking going on. So people commutative algebraists are trying to generalize things, and the algebraic geometers are sort of looking for characteristic special cases, and the algebraic geometers draw lots of pictures, and the commutative algebraists aren't doing that. And as much as it's sort of like listening to different people speaking English with different accents. So you say, okay, they're speaking the same language, but there really are differences. You can notice them. And so I want to say that the part of what we're groping toward, and because it's so formless and because it's so hard to articulate, it requires, saying some vague things sometimes, but we can perhaps say, yeah, there nonetheless are these differences here. We're trying to get clear and we're trying to articulate.
And are those differences of sociological differences or mathematical differences? Does the mathematics force those differences, or is it just you have different communities of people with different personalities, that's
well,
what's
it
raised
may
to me
be
by
that
your.
different people with different personalities prefer different modes of thought. Different styles of thinking. But I think you can still say the styles of thinking are different.
There's an intermediate step there, though. So they can also, you can also say, look, the methods are sort of unique to particular domains of mathematics, and that's they might be using the same subject matter more or less, but have characteristic methods that differentiate them. And that seems not just to be a mere sort of sociological fact.
No, yeah, absolutely. This is what I try to say by my simplified definition of analysis. This is where you have inequalities, but in algebra there are no inequalities. So there are some real differences between the methods. But of course, it's probably some kind of historical coincidence, that we call certain fields analysis and some other fields algebra. But on the other hand, I think there are some objective differences. Maybe it's better not to think of a discrete set, but what rather Marc suggested as a kind of continuum. We certainly can measure differences there, but maybe it's hard to I don't know, distinguish analytic number theory from, you know, complex analysis or something like this, but there's a certain distance for sure.
I think I'll withdraw my objection to 2. I think I'm kind of persuaded that they're all mammals and they look a little bit different. And if you really get to know your mammals, they look quite different. But that's just not
Maybe the distinction we need is between the mathematics and our knowledge of the mathematics. That a lot of what we're talking about seems to me to be having to do with it. I mean, the way mathematics develops, that's our knowledge of that mathematics. And there's some facts of the matter, although some, I guess, philosophers are less inclined to believe that than mathematicians. And then there's how we've come to understand those facts in mathematics. And that may account for a lot of that difference in flavor between different fields of mathematics. They develop differently, they developed subject, and it's sort of the mathematics itself that causes us to see these relationships between those different fields that's there in the mathematics. We just haven't learned enough about it yet until we finally do see those connections.
So what bothered me about the list without 7 is that when we're talking about mathematical depth, we have to be talking about depth, and I didn't see depth anywhere there. And the word depth means, you know, we're either digging deeply or we're thinking deeply, and something is happening that's deep. And you know, to a mathematician, if they're using the word depth, there has to be something that has to do with the word depth. And I didn't see that in anything except 7.
Well, 3 has an order. But what about definitional depth? Would that meet your requirement?
That's 7, right?
I think, yeah, I think 7 is basically definitional depth. That would be my explanation of it, right?
Yeah, 7 is the only
Yes.
place I saw depth.
Right, I think so. I think that's what Hardy meant.
It could come in 2 flavors. It could be sort of a conceptual depth versus a logical definition.
True.
But there's also depth of type, right? Natural numbers
Yeah.
are the lowest type, then real
Yeah.
numbers, then
Right.
sets of real numbers.
Right. That's similar to what Hardy said, except he's got these hard hierarchies the other way around. Upside down.
We've forgotten the category theorists, haven't we? That's the point. Didn't
Right.
we have a universal?
Well, David.
That struck me as a bit overstated.
You wouldn't put that in 1 or 4?
I didn't raise it, but it's suddenly, I like the argument that here some things you can point to and you can say, there's a category theory reason for saying that this is fundamental. And from that perspective, certain other things seem a bit contrived.
But it's the
And this is the
fundamental-
mathematical thing, so far as we can tell. It's not a subjective historical thing. Whether we want to keep it or throw it out is not for me to say. But,
It's the fundamental characterization of an object, right? It's not actually whether or not that is a deep result is a separate question in most of the senses we've been talking about what's deep, right? I thought that point was a bit orthogonal, and it seemed to me like it's an interesting notion of.
I'm just raising it. I'm not
Yeah.
defending it particularly.
What's the question? I
Be
didn't
educated about
understand. What's the question? The motion?
Maybe somebody better expert in category theory than I should say. Category theory provides you with universal objects, and this is the unique thing that does that because, right? And it points to a way in which certain objects are fundamental.
So there's one of the natural problems, and which actually Jim mentioned yesterday in response, is the direction you have there is wrong in the following way. There are things that turn out to be important, we can expect to be universal mapping properties, but there are a lot of things with universal mapping properties. You can get a lot of trivial universal mapping properties that are silly.
Okay.
And so it's the kind of thing that you might expect in a lot of cases to show up for things you find are deep, but the indication is just not that the converse just isn't going to work at all.
Okay, then we withdraw it. I'm happy enough.
Well, I mean, let me
No, wait.
play the devil's advocate. Let me propose a simplified version of, I don't know what this precise statement was. There's this joke that, the secret dream of every mathematician is to discover a functor. And I mean, in some sense, and there's some truth to it, that sometimes, if you find a functor, I mean, this is deep mathematics. For example, algebraic topology, it can be seen as it's just somebody found a functor, that maps the topological space to an algebraic group, namely the homology group. In some sense, this is a sign of deep mathematics.
Isn't
You
this
found this functor.
often what's going on though?
Maybe it can
Yeah.
be
Yeah.
subsumed into this.
I mean, you might even think that the right way of thinking about disparate fields is to say, well,
functor, yeah.
really we've got these different categories and we're tying them together.
Yeah,
We're
that's
talking
maybe
about
the
between-
precise definition of tying together. I mean, it doesn't apply in all cases, but sometimes it does apply.
Yeah. Yeah.
I wanted to just bring back something that, distinction that Andy brought up introduced in his talk, which was between consequentialist views of depth and the opposite of that was inherent.
The evidentialist ones, do you?
Well, the opposite of that was supposed to be there was something inherent, rather something about the consequences of the
Right. So the cosmological criterion is
Yeah.
in the theorem itself.
That's the opposite of the
Yeah.
And I was kind of the passage that Alasdair was good enough to embarrass me with, where I just throw a bunch of things together and say, they're all the same. What I was doing there was really trying to say there's probably not an analysis of X is deep if and only if blah blah. But there's no doubt that my tendency in that book is toward a consequentialist view. And so as you were talking about this, I was trying to think about it. And I thought that it might be partly a symptom of the fact that I was pretty much focused on 2 and 3 there in the deep as things. So I was looking at axioms, I was looking at concept formation. And I wasn't looking at concepts like the ones in 7 where you've got, I think in 7 you're talking about concepts you've already got, like real number or something.
Yes.
You're trying to figure out what does it
Yes.
take to, right? I was thinking of concepts like group, where you're starting out with a new concept and you're trying to decide what's the right way to tinker it. And I think, Jim, when you were talking about you've got different definitions around it, and you're trying to figure out which one is the best one. It's that kind of a case. It's not you're trying to capture some pre-existing imprecise idea with a precise definition. It's that we've got some job we want to do and we need some thing to do it, and so we're trying to tinker to get exactly the right thing. And in that case, the consequentialist thing is obviously what you want. And in the case of axiom choice, I've been trying to argue that what you want is consequentialist, but the opposite of that would be, in that case, some kind of intuitive or intrinsic kind of justification where, it's part of our concept of set or something like that. And I've been trying to argue that that's not really what we care about. But, so I guess what's funny to me now is that on the deep as things, there are all these ones that seem to me to be, at least primarily, consequentialist. But 1 through 6 aren't necessarily. I mean, 3 is the one you were talking about, and that's not, well,
Right.
I mean, I might want to say getting order out of chaos is a good consequence.
Sure.
But you want to say that's something, well, anyway, I just wanted to reintroduce that distinction and see what people think about it.
Well, I mean, it's not so clear to me. I mean, so it might be that part of what makes groups so powerful is the fact that groups show up everywhere. They show up in geometry, they show up in
Yeah.
topology.
Yeah, that is what makes groups so great.
And so, there's a sense in which what make the theoretical virtue of group as opposed to whatever else you might have.
But isn't 1 even already by itself a consequentialist idea?
The time
Which
as opposed to
wasn't
the
it?
showing up.
I mean, it has to do with what, if you have the should we talk about concepts for now?
Well, maybe I misunderstood what you were. I think
What I was suggesting was that trying to get together disparate fields for a concept really will have to do with the theorems that you can prove using the thing. So it will be a consequentialist idea. Right. So with my consequentialist bias, I'm looking back at 1 through now 7 and saying, where is the stuff that's not consequentialist and why?
Oh, I see.
So could you have a case of one where the concept, in order to have a non-consequentialist reading of one, you'd have to have a case where you brought 2 fields together in some way, but then weren't concerned with or didn't transfer results between them in any way? I mean,
Well, why don't you bring them together by
I-
doing some
I'm
general
more-
result that applied to both or something, because what we proved that would be the key.
And then you prove, and then you stop. Right. So that this was something that came up a bit yesterday, right? With maybe it was the classification of the finance symbol groups, and maybe it was something else we're talking. Where we had these things that we thought were deep, but were not productive past that point.
Mhm.
Right. Where getting to there, we had a deep result, and
Okay.
then we had it closed off a thing, right? As opposed to began a thing, and
Right.
maybe that's.
So that would be not a consequentialist thing,
Yeah, so the classification of finite simple groups maybe.
and
if
that
we-
was a 3.
I think we decided that, yeah.
Yes.
It
Okay,
fits
so
three.
it's 3 is where the locus of the non-consequentialist depth is.
Yeah.
Cause you've already got the consequent, you've already got the consequences in 3.
Oh, and 7 as well.
No, but say that I'm completely confused. 3 says that from relatively small premises you get this amazing thing. But I don't see. So I agree. At that
Premises
point, it's not
without order, you
consequential.
get a conclusion with order.
Yeah, but the
Yes,
consequentialist
exactly.
view is the deep thing allows you to do things in the future.
But that I take it is half the point of what these people are saying is here's this result, which tells you there's a field we ought to be going into. They don't stop with admiration of Summer-Rady's theorem and then get off their knees and go home.
Oh, that's, no, not Summer-Rady's, because that's got 6 and a number of other things. But I thought the example we had was Summer-Rady's opened up entire new fields.
Right.
I thought we had the classification of finite simple groups was an example where we brought order. We were able to get complete order for the collection of finite simple groups on the one hand, but there then weren't subsequent results we proved after that theorem that it sort of set off and was useful.
Oh, well, okay, well then, small point would be that that's not true, because what that opens up case by case arguments. The group must have this because we do it for the 8 families, and we do it for 26 cases, and that's all the cases there are, so we finish.
That's
what group theory is.
That's one of the reasons I was bringing it up. So I thought that was one of the examples, but I wasn't sure because I know we talked about things getting closed off yesterday, but I don't recall the example we used for it.
The only one I know that gets closed off is Hilbert's 5th problem. Sayre somewhere says, and I asked Andy Gleason once, nothing good came out of it. We had the result, and after that, nobody did anything to do.
No, that's false. I mean, for example, the Gromov theorem that I mentioned, there was an application
So
of
here's
a good example
I like these things.
from complex analysis, the Bieber conjecture. That was something about some univalent functions that was raised in the 1920s, motivated a lot of research for 60, 70 years. The problem was solved, and that was it. So it is generally considered as a very deep result, celebrated result, but in some sense it was an end point. Yeah. Nothing came out of it. I mean, a lot of things had to be developed to solve the problem, but after the problem was solved, in some sense the field was dead.
And where do you think, which of these are going to apply, or do you think there's another one we're missing?
That's a good question. I mean, where does it really fit in here?
Is that a multiple strata thing, potentially, or chaos, or?
It didn't bring any order into chaos. Hard to say.
There was the one we haven't put up there that's from a lot of the quotations that Alasdair strung together. And it's a very simple-minded one, that a theorem is deep, a proof is hard and long. Right? And it was striking the number of mathematicians who just said that.
Yes.
And that is certainly the case for this Bieber conjecture. The proof was actually hard and long. It got simplified. Now it's down to 3 pages. The initial proof was hard and long. And, it was an open conjecture for 60, 70 years. So.
Just to chime in quickly in defense of Michael, I do think we did have a conversation where the classification of finite simple groups was regarded as something which closed off research, but wrongly. We accept the friendly amendment that was
Was there a question about where the non-consequentialist moments were on that list of 7? Is 2 non-consequentialist?
Well, it deals with proofs, so in that sense it's consequentialist.
I guess I thought, you coined the term, so I
That's right,
obviously
yeah.
should defer to you.
So what I coined as is that a theorem is consequentially deep if if it's deep in virtue of some quality of its proof or proofs.
Some quality, I wrote down as, some quality of its
Isn't that
consequences.
Oh, wait, sorry, that's
Or
what I
of
was
the
calling
consequences
evidentialist.
of its proofs.
Consequentialist is what it was useful for, sorry.
Right, so that's
Yeah.
why I didn't think that 2 was consequentialist. I thought it was
Yeah,
sort
right,
of
I'd call it
whatever the
evidentialist.
opposite of consequentialist
Yeah.
is, antecedentist.
It might just be stuff.
It might matter that the pen you're thinking about deep concepts. So if you think of a deep concept, what makes the concept deep is that it can be used in producing proofs, and so then 2 might seem consequentialist. But if you're thinking of 2 as a feature of deep theorems, then it's not consequentialist.
Yeah, I think it was my focus on concepts, was giving me a different picture of things.
There's an interesting example, which I don't think has been brought up, of a case where what I think is a deep theorem finished off a field, which is invariant theory. I think Hilbert's proof there, and maybe it was mentioned earlier, but Hilbert's basis theorem for invariance kind of finished off invariant theory. It was a very active field, but people just sort of stopped working on it after Hilbert finished everything off. It's not to say it's going to remain dead forever, because people have been trying to revive it. But that's an interesting example of a deep theorem which did kind of finish off an area at least temporarily.
So, Mario mentioned finding a functor. I mean, I think one case that kind of thing that's often considered deep that hasn't come up at all are duality results. So the special class of functor that's contravariant and has a essential inverse. Certainly, I mean, does many of these things sort of, more clearly than anything else one might say. So if you think about the stone duality theorem of perception, so you have Boolean algebras on one side and stone space on the other. It's this link between algebra and topology, and it's, it turns out it's not just a link, it's about as intimate a link as one could have with the same category, except you just switched all the arrows around. And certainly surprising. There's a sense in which it certainly doesn't open up a new field.
But isn't that a central case, a paradigmatic case of trying to get to disparate fields?
It is a paradigmatic case, yeah. But no, I think, yeah, no, that's exactly right. I mean, I think paradigmatic in a way that helps us see why the notion of tying together disparate fields might not be totally useless to us.
And number 4, organizational power.
Yeah. It's interesting to ask whether or not that requires or admits an impure proof. There's another case where if you understand that as a result of category theory, then well, I guess I'm not sure. I mean, so what could you understand that as a result of? Is it a result of category theory? Is it a result of the theory of Boolean algebras? I think it really does require an impure proof in some sense, right? Because you need to show something about the arrows of each of these categories as arrows, as homeomorphisms of stone spaces, as homomorphisms of Boolean algebras, and then show something about the functor that relates. So we're past 6 o'clock. I don't want to end discussion prematurely, but if there was a sort of long pause just then, stand here and wait for someone to say something.
I think we should thank you all very much for
Here, here.
folks here.
Yeah.